Great, thank you all so much for joining us here this afternoon. We are going to try to take you on a journey. As I start, think about what we understood 30 years ago. 30 years ago, most of our understanding about sea level came from a smattering of tide gauges in coastal regions around the world. Most of what we understood about precipitation came from rain gauges or ground-based radars, which means we understood rain over land, but had never seen it really effectively from space. So we're going to try to take you on a journey today about what we've learned in 30 years of doing Earth observation from space, and we're going to focus on the water cycle. Let's see if this works. Oh, no, wait. There we go. So, simple framing. What have we learned about how water moves around our home planet? Because it is so essential to our lives and our livelihoods. So, please join me in welcoming my colleagues and friends from space agencies around the world to help tell this story. So let me welcome to the stage Selma Trachali from CNES. And Eric Laliberté from CSA. Simonetta Kelly from ESA. Godella Rosner from DLR. Francesco Longo from ASI. And last but not least, Koji Terada from JAXA. All right, so we're going to tell that we have a story for you in 4 acts. The first act, we will talk about sea level. It is the most obvious indicator of climate change, and it is having impact around the world. And so to introduce what we've learned about sea level rise and sort of how we did it, I'm going to ask Selma and Simonetta to start us off here and talk to us about the historical partnerships, what we've learned, and where we're going.
Yeah, thank you very much. Good afternoon, everybody. It's really a pleasure to be here with you today. And of course, you are here an important and amazing sea level rise accuracy that has been reached over the 30 past years. And yesterday we heard from several plenary sessions the importance of sea level rise and its impact. This story has started within Topex Poseidon experiment mission between NASA and CNES in 1987. And it has been launched in 1992. And from the beginning, the science team plays important role in very close cooperation with the project team on both sides. And this group is now an international science group, which is called Ocean Surface Topography Science Team, which yearly meets and attracts hundreds of scientists around the world in order to address the state-of-the-art of altimetry, science, and application. And the challenge at this time was really, really high. As you mentioned, we haven't at this time space data. And the objective was to demonstrate that altimetry measurements could be made sufficiently accurate and precise to detect sea level variation of 10 centimeters induced by the ocean circulation, global circulation. And in parallel, ESA was developed ERS-1. And very quickly, it seems very important for international agencies, ESA, NASA, and CNES, to jointly invent a new concept, which is the virtual constellation that has been approved and formalized through the Committee on Earth Observation Satellite, CEOS, and which is really important in order from the end user point of view and science point of view. This is important to have data harmonization and data calibration. And the success story, due to the, of course, full commitment and joint trust of each other, has been successfully pursued with JSON series and, of course, through operational mission at Copernicus level. And Simonetta, perhaps you could tell something on Sentinel-6, Mike Friley.
Sure, but certainly welcome to everybody to this session. I think that sea level rise, as Karen pointed out, it's a very good example of the international collaboration, and also the collaboration we've been having for decades on this topic among agencies, not just in Europe between national missions and European ones, but with Sentinel-6 launched in 2020. I think this collaboration really expanded to the Commission, EUMETSAT, NASA, NOAA, and of course the French. And this, I think, it's not just symbolic, it's also the results of the capitalization of a collaboration which really goes on the technical level, but more widely on the topic of climate, on the topic of environment, which is the one of the session here today. You see here in the graphs the mean increase of the sea level rise, and this is something which had a steady evolution, which is measured by all measurements on all missions that we've had. We spoke about the research ones like ERS, but now with Copernicus Sentinel-6 we've gone to operational missions, so missions which are done in series in terms of supporting operational needs of the user communities, which are not just the science one, but also overall largely the marine community. What's next? I think, first of all, what you see here, it's a trend in terms of increase of the sea level rise. Unfortunately, this is due to what is happening currently, and we heard a lot about it the last 2 days. It's melting of the ice. It's also temperature increase, which of course provides for expansion of the oceans overall. And this is all measured by very, very advanced instruments, no matter if it's the altimeter or the SAR on board these satellites. What's coming next? We have 3 more missions, again in collaboration coming up. So we have Sentinel-6C, which is going to be launched, but B before that. And we, of course, have other missions like, for example, the Crystal mission in the context of Copernicus planned for 28. And then here, still in the graph, what you see is the results of what's happened in the last 2 weeks. So you see the comparison between 22 and 23, and really this temperature increase that we've seen that is hinting to a new phenomenon of El Niño. So very important to look at that. But the puzzle is not just the sea level rise and temperatures. We need to have also better geoid of the Earth, more precise one, which is what we aim at doing with the new gravity mission and GGM and the collaboration with NASA. Because if you understand the precision of the geoid, you can also better understand the variability of the sea level rise.
Ah, okay. So sea level, we now have a 30-year record that's giving us the rate, and that rate seems to be accelerating. It comes together from multiple missions that are directly measuring sea level, but also to do that we need the reference frame. Right, and let's...
Yeah, I would like also to come back on this important result. Simonetta mentioned the sea level rise. Of course, it's a fact. But the scientists would like to understand more why this sea level rise is rising and how sea level rise is rising. Explain that. And this graph showed from an important project conducted under ESA CCI Plus Climate Change Initiative, dealing with the sea level budget and energy budget, the contribution coming from 50% of sea level rise is due to continental ice melt and 34% due to ocean warming. This is important to understand in order to affect, of course, the contribution of each compartment of the Earth system, which is a really complex one. And this is really a very unprecedented recent result. The second aspect is dealing with the energy budget, and one of the important proxy of the energy budget imbalance radiation is the hot flux ocean. We which represent more than 90%, which is very good, which is showed here on the right side. And again, it's a combination, as Simonetta mentioned, between several assets and data, space data, which are really crucial, altimetry, but also the GRACE and the GRACE follow-on measurement and Gautier also measurements.
Thank you. You know, it's a really interesting part of the story here. We've talked earlier this week about trust. And I think part of the important story we can tell is we know it because we measure it, and we measure different parts of the system, and when we can put that together into a coherent story, we think we can trust that we understand, right? So it's not just the what, it's the why, right?
Yeah.
And you mentioned about 90% of the heat, the excess heat that's trapped in the Earth's system, is absorbed by the oceans. Most people don't understand that, and that's contributing to the sea level rise. Well, so sea level, right? That's the first part of the story. Let's move on to the second act. We're here to talk about fire and ice, so let's move to the higher latitudes. Let's talk about ice. So to start this conversation, let's talk about ice on land. And Gudella and Francesco, I think you were going to take the lead on introducing this topic.
Maybe this is yours.
Yeah, so I just wanted to add to what Salma said, and you already introduced GRACE and GRACE follow-on, and really adding to this whole system and understanding of what is going on in our climate. And GRACE, since 2002, has delivered us very valuable data on the whole water system, let's put it that way, and really adding the fact to the sea level rise that it's due to, or up to 60% due to ice melting. So, and this is an information that GRACE was contributing to the whole story. And what we see here on the graphs is the dramatic melting, especially of Greenland, adding even more to the sea level rise than the melting of the Antarctica. And so seeing this continuity and seeing the seasonal changes and having in mind that sea level rise is one aspect, but also the melting is also adding to the ocean circulation, it's more and more important to understand these processes. So it's really important not only to have this view in the past and the 20 years we have until now from this data record, but also to prolong it into the future. So I think that's why we are all working on prolonging the story of GRACE and GRACE follow-on with the Mass Change Mission and then NGGM to have a continuous insight into the whole water system, because ice melting is one of the major topics, of course, for the sea level rise, but the whole mission also contributes to our understanding of terrestrial water storage and where the droughts and where flood risk is increasing. So I think it's also something to add to the system, and as you said, to validate also, in a sense, to see how everything fits together. Yeah.
Let me say something, because I want to say that NGGM, our European mission, started from the end, is an important part, contribution to climate change. But let me be more ambitious with the NASA contribution mass change. In MAGIC, we can have a constellation with two pairs that contribute a lot on our scope on mass changing in the world, understanding about the climate, about the increasing level of the sea. But this big picture, as a puzzle, is composed by small parts. Then I want to focalize on what is important part of this puzzle, the glaciers. Mm-hmm. The glaciers are alive, are not something static. They move, they melt, and also are impacting from warmer air and warmer ocean, right, from subsurface, and also the tidal effect. What we measure in this case, all the models considered the grounding ice, the junction between the ocean and the ice on the ground, as a zero melt. Yeah. Then, an important discovery using not only data from one asset, but using RadarSat, Cosmos SkyMed, TerraSAR-X, and also the data from Friends of ISI, was impacted on our knowledge of what's happened at the grounding line, grounding zone, the point that is most affected from the melt. This is an important result because, let me say, the goal is science, the goal is application, but the goal is the societal benefit. And the glacier, the protection of glacier, are very important for a possible service in order to monitor this structure. Eric, it's your turn.
Well, thank you. It's a beautiful example of the collaboration that's needed in order to get this overall understanding. So when you talk about glaciers, I know we're getting close to 30 years of RadarSat mission. And so the long-term series, the long-term observation is required in order to gain that better understanding. And the latest of our mission, the RadarSat Constellation mission, was designed so that we can observe the Arctic like 4 times a day. But we're adjusting that according to our collaboration. We're adjusting the standard coverage, as we call it, to monitor the Antarctic, and I believe it's 62 sites for glaciers that are melting. So that contributes to the wealth of data for us to consider.
Yeah, go ahead, Selma.
Yeah, it let me to say that we will see perhaps amazing today unexpected results from the new generation of altimetry mission.
Oh, yeah.
Yeah, from the surface water ocean topography. We spoke a lot about sea level rise, but we know that the impact of climate change on water cycle is, of course, affecting the continental parts, which is the fresh water. And the scientists learning from these 30 years of altimetry requested from the space agencies NASA and CNES initially to have a global observation at very finest resolution, 10 times better than nadir altimetry, in order to tackle, of course, the smaller scale where the ocean dynamics are occurring, and we are currently missing them with the current observations and missions, and they believe that are the key factor in understanding the climate change and ocean dynamics. This is for the ocean. But for the first time, we will have a global observation covering nearly 90% of all Earth's water. Rivers, like lakes, reservoirs, and all water body that could be covered by the mission, with an unprecedented also accuracy. And potentially, those new breakthrough measurements, wide SWAT, interferometry radar with really unprecedented accuracy, will open the door for monitoring the ice sea in Antarctica. But more important, yesterday we had the importance of impact of climate change in coastal zones. And today we know from science results and activity that we are facing issues in order to approach those coasts. And SWAT will open a new era with these new measurements covering, of course, globally for the first time, many of the Earth cycle, water cycle components.
Thank you for mentioning SWAT. It is the next generation in measuring sea level, but also extending that altimetry measurement to inland water. So the first ever global inventory of inland water. And if you stay till the end, you'll see some new results from SWAT that have not been seen publicly before.
And if I may, SWAT is, of course, a US French bilateral mission, but we are supporting from the European side the science assessment of the data from SWAT, and in this process we're also looking at this as a reference model for Sentinel-3 Next Generation, which is one of the next Copernicus mission that we'll have to develop. So again, an example of international collaboration and perspectives for future measurements and better ones for everybody.
And a new discovery mission making its way into a long-term sustained kind of capability. Well, let's stay in the Arctic for a few more minutes, and let's talk about sea ice. So, Terada-san, what do you see from space about sea ice?
Yes, thank you, Karen-san. Please. So the sea ice extent. Next, please. Yes.
Wait.
Yes. The sea ice extent has been rapidly decreasing in recent years as global temperature have risen. As sea ice extent is very important, space agencies are continuously monitoring it from space. These pictures are long-term variation of daily sea ice extent in the Arctic and Antarctic Ocean observed by the passive microwave imagers. Microwave remote sensing from space is only tool that provides continuous, consistent, and comprehensive information on sea ice changes in polar regions. Although the decreasing trend of sea ice extent in the Arctic is clear in recent 40 years, the Antarctic area sea ice extent shows no significant trend because of regionally opposing trends and large internal variability. We should continue observations on the change in the polar region. For example, the recorded minimum of Antarctic sea ice extent has been updated several times in recent years. JAXA provides data of a variety of satellite measurements from passive micro images. These data aim to capture sea ice concentration and sea ice extent trend in the polar oceans on a daily basis from 1978 to the present.
Thank you. Any other comments on sea ice? All right, so far in our story, we've talked about sea level rise. We've said, all right, from our observations, we not only know what the sea level rise is, but we know that about 2/3 of that comes from water being added, water that was trapped on land, now going into the oceans. 1/3 comes from heat and expansion. We know how much ice has left the ice sheets on land, and we know that we can see the reduction in sea ice, particularly in the Arctic region, both in thickness and in extent. That's not important, that's not driving sea level, but it is an important climate feedback, right? Because particularly in the Arctic, sea ice reflects the sun's energy. So the less sea ice, the more the oceans are absorbing the energy. All right, so those are our first two acts in this story. Let's move on to the third one. Let's talk about what's going on in the atmosphere, because 30 years ago or so, we had really very little understanding about global precipitation. So let's start with Selma and Terada-san talking about precipitation.
Yeah, just a very quick introduction. I think this is also a very excellent illustration of the international cooperation which started 20 years ago between NASA, JAXA, ISRO, and CNES. And from CNES perspective, from the beginning, the French scientists were involved in TLMM, precipitation, and we signed a memorandum of understanding between NASA and CNES on GPM constellation in order to contribute with megatropic data. We spoke yesterday a lot about the storm, the extreme events, and we understood with this previous decades of research that there is a strong need, a new challenge to address in order to retrieve the vertical velocity in convective systems. So we have the consistency of precipitation measurements. This is globally, of course, but we need to move further in terms of research activities in order to tackle and to understand those local processes, of course, having a lack of data. So the Atmosphere Observing System program leading by NASA, with a key contribution from CNES on this important aspect of convection. So from precipitation to convection era, that's what is now happening for the next 20 or 30 years.
Right. It's really important because all the water we need to live on land is delivered to us by the atmosphere. So understanding how water is moved in the atmosphere and how those storms intensify is critically important. Trada-san.
Yes, JAXA contributes to the international collaboration for global precipitation observation by our precipitation radars. JAXA provides the world's first space-borne precipitation radar on the TRMM, launched in 1997. Also, JAXA provided our precipitation radar to the GPM core observability, launched in 2014. The precipitation radar observes three-dimensional precipitation structures like CAT scan in medicine, and we can explain the regional difference of global precipitation system more sufficiently. The reference of precipitation radars led to significantly improve the estimation accuracy of precipitation distributions by multiple microwave radiometers being operated over the world, and led to create a global real-time precipitation map.
Thank you. So Selma, you said it, right? We're moving from an era of really focusing on precipitation to understanding the processes, the why is the precipitation what it is, why do storms intensify, when and where they do, and actually many of us are participating in the next mission to really go after some of those questions, the AOS mission that you mentioned, where we'll be looking at the relationship between aerosols, clouds, and the storms that form. So really exciting time in moving forward our understanding of the atmospheric transport. Go ahead, Eric.
Yeah, I just want to add that it's not us just on stage that are interested in this, right? It's the science. And I know that you didn't mention the atmospheric observing system that you're leading,
I know.
and that you invited some of us to, all of us to participate in some way. In Canada, it's a consortium of 14 universities. So scientists, like the science is important, the understanding. So I think you're right. It's all these, the next step is really understanding all these processes and making sure that the information then can be transformed into usable data and policy making eventually.
And this becomes especially important in coastal communities where the combination of sea level rise and storms is a double whammy. It's a double impact. Selma, you wanted to add something?
Yeah, I completely agree. Of course, all those observations were requested through the science community. When looking back 20 years ago, it was not the case. But I would like to say something, an additional important comment. When the scientists requested the mission for some observation, they imagined that they will only fit those requirements or those objectives. Looking back to megatropic in the GPM constellation, the assimilation of those precipitation products and measurements allow really an improvement of the forecast of the numerical weather prediction. Right. Which is also the way that from science to applications to better forecast is a key aspect that will also be awaited for the SWOT measurements in order to have a better prediction with the finest observation. And the science community, internationally speaking, is preparing a new generation of models, but either in ocean, hydrology, or coastal models, because they found there is a really unknown physical process, and we are missing some really key data to feed with those processes and having better prediction, as we rely today on weather forecasts between models and the right data. So, of course, I agree.
Yeah.
Well, you make a really interesting point, because 30 years ago, I'm heading into dangerous territory here because I don't know these numbers precisely, but I think it was true that 30 years ago, the one-day forecast was only as good as the 3-day forecast is today, right? There's been dramatic improvement. And in fact, my colleagues at NOAA would tell me, if today you like your weather forecast, you should thank an oceanographer. Because this relationship between what's happening in the oceans and the weather really, we're here largely to talk about climate today, but it also has an impact on those real-time weather forecasts. Wonderful. Yeah, go ahead.
Yeah, the largest factors of uncertainty in climate models are cloud, aerosol, and precipitation process. So JAXA would like to address to understand the process with international partners. This effort is important to predict extreme weather events that appear in each region as an effect of climate change. So first, a giant mission with ESA ASKAR satellites, so capable of observing a cloud and the aerosol at the same time. It carries JAXA's cloud profiling radars, capable of monitoring the vertical structure and monitor motion of the cloud by the Doppler velocity observation. Next, AOS, mission of NASA. JAXA participates in AOS with the next generation precipitation laser to observe the vertical structure and the vertical motion of precipitation by the Doppler velocity observation. The process of cloud and precipitation will be clear by observing the vertical information.
Thank you. Yeah, it's a really important point. Going after those processes between aerosols and clouds and the climate feedback mechanisms, that's a key aspect of the next generation mission. And we'll only be able to really get to those questions because we're making all those measurements at once. And this is another key thing, I think. It's not always about the next best instrument. Sometimes it's about having all the right measurements at the same time, observing the same thing, give you insights into the processes that we really need to understand how climate's evolving. Okay. Everybody,
let me say something regarding the importance of this prediction, also considering that the flooding event, the disaster event connected to flooding is more than 70% of the disaster that we have in the world. We have in Italy now, and this opportunity to receive good prediction in order to give the right alert to the population and to increase the level of the risk and also the action from the civil protection must be accompanied, of course, on the evaluation from space, also of the perimeter of the areas impacted from this type of event. Then is all a mechanism that at the end starts with observation and close on services for civil protection, for societal benefits.
You know, it's really important and interesting that you mentioned flooding specifically. Earlier, Selma mentioned SWOT. One of the things that SWOT will be able to see, we've talked about it will measure the height of inland water bodies. That includes temporary ones, in other words, floods.
Yes.
Right? So for the first time from space, for many years we've been able to see where the flooding is, but we've not been able to characterize the height, how much water is there. SWOT, because of its spatial resolution, in real time, when we're dealing with disasters, will give us a view of how much water is there as well. Go ahead, Selma.
Spatial resolution, but more important, for the first time, I would like to say a bidimensional image. I mean, SWOT has two SWOT, 50 kilometer and 50 kilometer, which means that for the first time, as you mentioned, Karen, we will have the measurement of flood water elevation. Really in an unprecedented way and vision.
Fantastic.
Great. Okay, so we're coming to the fourth act here. We've talked about the oceans. We've talked about the atmosphere. Water. It's essential to those of us who live on land, right? We need it to generate power. We need it to grow food. We need it to drink. So let's talk a little bit about water on land and this is an even easier place where we can talk about how the information serves people. So kicking off this part of the conversation, let's go to...
It's our table.
Yes, to Godello and Francesco, take it away.
Yeah, thank you very much. Yes, it's a strong cooperation between us and DLR that focalize on opportunities on hyperspectral, but focalize on what? On water. Water is vital for life on Earth, and water, we have to understand the characteristic and the situation of the water, also considering that must be safe, clear, for consuming. Then, using hyperspectral, our effort is to start understanding the status of the water, starting with the first element of the lakes that are the first elements where the demand for also for consumables, but also for agriculture want to. And let me say, we see in the effect of industrialization of the population near the lakes and also near the sea, and the effects are very clear, considering that extracting the spectral signature from our satellite, we can see a lot of elements or pollutants in the sea, the turbidity, the total matter suspended, all the elements, the chlorophyll, all the elements that give us indication about the health status of our water.
Yeah, and well, I think this hyperspectral information that we're providing with the missions, and that will be prolonged then also with CHIME and SPG, is really essential to have a better understanding of the biochemical processes that lie within, well, not only water, also other aspects, to really quantify and understand the effects that are coming with the increasing temperature, changing ecosystems in the water, changing carbon cycles due to these effects. And it will be essential in a very practical way for the people on the ground delivering drinking water or watering their agricultural fields and so on, but also in the understanding of the climatic processes. I think there are these two dimensions we have, and I think what we have shown already through this discussion is that Earth observation puts us in the place to have a very holistic understanding on each and every process of the planet, to really have an overview and have a substantial insight in all the processes. But we need to connect to the scientists, to the modelers, and we see this already with the IPCC reports that build very much and much more on the Earth observation data that has been included. And on the other side, taking into perspective the increasing risk that is coming with climate change and what it means for the practitioners is really to look for the applications and well, putting up services, putting up decision support to policymakers, but also to resource managers in many different markets. So I think there are these two aspects. Earth observation is really a key asset, key instrument to allow us to have a better holistic understanding, but we need to bring it across in these two directions to make it really actionable information and giving trust to what we know about climate change.
Yeah, no, please.
Go ahead.
No.
Oh, I was going to say it's my turn to express my passion
Yeah.
for SWOT. Because
Thank you.
but it's just what you said, Godela, when you mentioned that we need to look at, and Earth observation can contribute a lot, and we're very excited because you said water is essential for those of us that are on land. It's also useful for fish and stuff.
Oh, yeah.
But so water is life, but water is also energy. So SWOT, temporary phenomena, rain is not falling at the same time it used to. It used to be in snow. It used to be. So the reservoirs that are used for hydroelectricity, it's a completely different management situation. And even we're talking about the water cycle, you could talk about the biodiversity, We have lakes in the north that are not monitored, but now with SWAT will be, that can drain in a day and change the ecosystem completely. So it's something that we're not seeing right now with our means of observation. So,
yeah.
Go ahead, Selma.
I completely agree, and I think often we missed within many conferences the importance of water as a nexus for energy, food, and security and health. And I think SWAT, yes, is opening this important era and door. And looking back to what has been said by Godela, I completely agree. I think we have to manage to make a strong linkage between science and what could be a cure and develop in terms of application. That's why, from the beginning, jointly with NASA, within the SWAT project development, we have decided to have a dedicated preparatory program, both in science and in preparing the future upcoming applications, among of them, of course, hydroelectricity, but also navigation over the rivers, over the ocean, due to the very finest measurement that will be, hopefully, be available to the end users.
But because our ambition has no limits, we are supporting in ESA the CHIME Sentinel for hyperactive service in hyperspectral, and at the national level, reducing one of the elements of the parameters that, as requested by our users, the resolution of the hyperspectral to 10 meters, as requested by farmers, by all the persons that live with agriculture, with water. Then it is important for the future what we have in plan to do.
Yeah. Before we leave land, let's spend a minute on agriculture. I think, can we bring up the next slide? There we go. So we wanted to talk a little bit specifically about the interplay between water and food security.
Yeah, I'm proud of about this mission, the results of this mission, because water, the use of water is very important. And this mission, SBGTIR with NASA, but also Trishna, but also LSTM, all these missions are contributing on efficient use of water, but oriented, let me say, on the, could you see to the lower part of the screen, on the real use. My dream is to have a farmer with a smartphone in order to understand the water needs of the plantation, in order to an efficient use of the water. And in this case, this mission that uses EcoStress, fantastic mission on ESS as a precursor, will have not only surface temperature, but joining also visual and near-infrared NDVI in the simultaneous scene. And this is a very giant leap in the sense of reconstruct evapotranspiration. That is the most important part of the cycle of the water, evaporation from soil and transpiration from the plant. Right. And this part is very important to understand also what we want to understand with NGGM, what is missing in this cycle that go in groundwater. Then everything is closing in this mission.
Yeah, that's exactly right. I mean, in the Western United States, we have real challenges with water management, and we have already taken steps in this direction. We have applications that farmers can use right in their fields to assess how much water their field has used, and they use that to adjust how much they have to irrigate, and it's resulting in tremendous efficiencies. So we're down to our last 5 minutes here. Did you want to go ahead?
I think what we see already from all the applications that have been mentioned is that nowadays we think Earth observation much more from the end user and end usage. So what you said about SWOT preparation, preparing not only science but also applications, I think that's becoming true for more and more missions. So for example, what we are preparing with PRISMA and NMAP directly feeds into preparations then for CHIME and SBG, and there will be many more examples like that. So I think we're working on Earth observation much more closely nowadays and coming from the end user and the benefits that we want to show and bring to practice with our missions.
Sure.
Perhaps a last word. I agree totally, but in the meantime, I don't want to make a misunderstanding from the audience. I think when we are developing new measurements, like the one of SWOT or for the evapotranspiration, either from SHIME or SBG or Trishna or LSTM, there are huge efforts to put there in order to tackle new physics and to derive from data the right data products and information knowledge. Because yesterday I was a little bit surprised. We were speaking about data. But what end users are waiting are information products and knowledge products. But to reach this step, believe me that for SWOT, and I think I see Parag in the audience, more than 20 years of effort and sustained support from the NASA, CNES, CSA, also with a strong preparatory program, in order to allow to address those new measurements, addressing, this is a big picture, global picture, looking to local things. So it's a new generation and new ways to address, and more important, as you mentioned, Karen, how we could handle those data and put them in a very easiest way to the users, including scientists. And believe me, there is still a big training to do in order to allow them to handle those data. Thank you.
Thank you. So I promised you that if you stuck around, you'd see some new results from SWOT. We're down to just a few minutes, so I want to show those results now. So this is, as you know, SWOT was designed largely to measure surface height at a very fine spatial resolution for water, both oceans and inland water bodies. Turns out, when you fly a mission globally, you get to see the globe. And here we're looking at some new results looking at sea ice. You want to say a couple words?
Yeah. I think this is really a preliminary result. This is the first time we show that. We were not expecting, this was not the main objectives of the mission, to monitor the sea ice. This is ice breaks that open, move, or close every day because of the ocean currents in the Antarctica. On the left side, you have the radar power, and on the right side, you have the surface heights. And of course, there are several tens of meters of variation that we have not developed a specific processing algorithm fitted to sea ice, which means that if needed, we have to make some effort in order to make what we made for hydrology, for example, processing to address the phase of some technical elements. And of course, the iceberg is surrounding here by also a blue area without ice because there is a submerged part. So this is a really amazing animation because we are today in SWOT, what we call in the fast sampling phase, which means in the Calval process, we have 2 periods. And this is 1 day revisit period in order to allow scientists and the project engineer to really calibrate the instrument and in the meantime to acquire a huge amount of data in order also to train and to test their models that they are aiming and they are developing for a long time. So this is our pleasure, NASA and CNES, to show these first preliminary results, but there is, of course, a plan for many other events and communications. Thank you.
Thank you, Selma. So, you know, I like ending on this example because serendipity is also important in what we do. Every time we launch a new capability with one particular focus in mind, we also find that we learn things about the rest of the system. And that's part of the reason that we're always looking to advance, because we know what we're trying to learn, but we don't know what we will also learn. So we're in the red zone here, so let me sort of wrap this up. This is a story I find myself telling a lot, the story of the intensification of the water cycle as a result of greenhouse gases and warming of the climate. But we don't tell the story often enough about how we know what we know. Gets to the trust, gets to the confidence. So today we tried to walk you through what we've learned and what we're hoping to learn next. I hope you took away from this that, point one, this is only possible from space. You can only have developed this understanding from space. Point two, you can only do it. We could only do it together. It's more than any one country. It's more than any one continent can take on by themselves. So it's been a tremendous journey so far, and we're looking forward to the adventures ahead. And then, of course, we're all working together. We could have had a whole additional session on how we're trying to drive all of that information into use. We mentioned some of that to you again here today. So deep thanks to my colleagues. Thank you all for joining us for the conversation. And I think that's all we got, right? We're going to get the hook. All right. Thank you.
Thank you, Karen.